Welcome everyone. It's a pleasure to have Professor Florian Beutler here today. Thanks a lot for accepting our invitation. Florian is a professor of observational cosmology at the Institute for Astronomy in Edinburgh since 2020. He had his PhD at the University of Western Australia, then he was a postdoc at Berkeley and then Portsmouth, and became faculty in 2017 in Portsmouth. Florian is working in the field of cosmology statistical methods and is using the distribution of galaxies to test cosmological models, focusing on dark energy, dark matter, and inflation. Today, we'll present cosmology with the Euclid and the Dark Energy Spectroscopic Instrument. Florian, please, you can start when you're ready.
Thanks a lot, Eleonora, and thanks for the invitation. It's a pleasure to talk about the DESI results. So I wasn't sure how long the introduction should be. So if there's anything unclear of what I'm saying here, just feel free to interrupt me at any point and ask questions. I think I can see if you raise your hand or just unmute yourself and ask any question you have. So the plan here is for me I will give you a short introduction into galaxy redshift surveys, and then I will introduce DESI and sort of a slew of other galaxy redshift survey data sets which we have available right now. And then I will talk about the cosmological interpretation. Okay, so let's get started. So galaxy redshift surveys. What is the galaxy redshift survey? Well, what we are trying to do here is we are trying to measure the 3D distribution of galaxies. And we are using these galaxies to trace the underlying matter density field. So here on the right-hand side, you can see a galaxy redshift survey. Each black dot is a galaxy. And these black dots, they trace out density perturbations. These density perturbations are what we are trying to measure. And the reason why this is interesting is because we know the initial conditions of these density perturbations. We know this from the CMB on the left-hand side. You can see an image from Planck. So we know these density perturbations at time equals 0, as measured in a cosmic microwave background, and how these density perturbations evolve from time equals 0 to something like 10 billion years later in our galaxy redshift survey. That depends on the background cosmology, on your cosmological parameters. So you basically compare the density perturbation which you can see in your galaxy redshift survey with the density perturbations you can see in the CMB, and comparing these two allows you to constrain your cosmological model. That's the general idea. And I will explain this in more detail later when I talk about Baryon Acoustic Oscillation, which is the main observable I will talk about here. Okay, so I will skip a lot of details here, but one aspect I should mention is that what we usually do when we analyze this galaxy survey, which is basically a point distribution, right? So we use these galaxies to trace the underlying matter distribution. We do not care about the properties of these galaxies. So whether you have an elliptical galaxy, a star-forming galaxy, it doesn't matter. We just use them as tracers. So these are basically points. And we basically end up with a point distribution. And we do not analyze the point distribution directly. We usually compress that information into a summary statistic. And the only summary statistic which is important for this talk is the 2-point correlation function. So what you do here is you take a volume element in your 3D volume, which is populated with your points, and you measure the density of galaxies in that volume. And then you normalize this by the mean density, and this gives you the overdensity field, delta here. And then you calculate the 2-point correlator. Basically, this just means you take the product of deltas, which are separated by a vector r. And these brackets here, they just mean that you take the ensemble average. Yeah, this gives you the 3D correlation function. And then if you don't care about the orientation of this vector r, you can spherically average this. And this gives you the correlation function, which now depends only on the amplitude r. So that's a 1D quantity rather than a 3D quantity. Much easier to analyze. For some reason, there is actually an anisotropy there, which you would lose if you just look at this one-dimensional correlation function here. And this anisotropy has to do with the observables, which we use in a galaxy redshift survey. So we use angles for the angular position of a galaxy on the sky, and then we use the redshift for the radial distance. Because we use these observables, there are anisotropies with respect to the line of sight, which we might be interested in, and I will talk about one of those later on. And for that reason, what we usually measure is the 2-dimensional correlation function, which depends on the separation r and on the angle to the line of sight. Mu is the cosine of the angle to the line of sight. And then we usually multipole expand this using the Legendre multipoles here. And this gives us the correlation function multipoles. So the main point here is that we are compressing this information in our point distribution into a one-dimensional quantity, the correlation function multipoles here. But we are using two of these quantities. We use the monopole, where this L is equal 0, and the quadrupole, where this L is equal 2. So we compress all of this information into these summary statistics, and then we analyze those. You can do this in configuration space, where you would use these correlation functions, or you can do this in Fourier space, and then you would use the power spectrum multipoles here on the left-hand side, and these are connected by a one-dimensional Hankel transform. In principle, you have the same information in both of them. I will show you some power spectra, but the DESI analysis actually has been done in configuration space. So we use the correlation function for this analysis. And of course, I should mention that the two-point correlator is just sort of the simplest way of how you can try to extract information from this point distribution. My main work actually concerns sort of using higher order correlators and extract as much information as you can from this point distribution. But for this talk, I will just focus on the two-point correlation function. Okay, so I will now introduce a couple of galaxy surveys. So before we started DESI, the largest galaxy redshift survey, at least for cosmology, was the BOSS Galaxy Redshift Survey. And BOSS observed about 1 million galaxy redshifts between redshift 0.2 and 0.75. Had a sky footprint of 10,000 square degrees. And you can see the SDSS telescope in New Mexico here on the right-hand side, which was used for this. And the way how we obtain the redshift is we have to put a fiber at one galaxy and observe the light from that galaxy, and then look for absorption lines or emission lines or some other feature which allows us to get the redshift. And to do this, what we did in BOSS is we had these aluminum plates, which you can see here at the bottom. And in this particular case, there are 1,000 holes drilled into this aluminum plate, and somebody at the telescope actually had to put these fibers into these 1,000 holes. And then you had this construction of these fibers together with this aluminum plate, which you put into the focal plane of the telescope. And then you observe for half an hour, depending on the observing conditions. And then you will get 1,000 spectra, and then you can search for your features in the spectra, which allows you to get the redshift. And then you take another aluminum plate, and you do the same thing. And of course, the holes in the aluminum plate are exactly where you expect these galaxies to be in your focal plane. So this is how it was done in BOSS, but with DESI, we have moved on a little bit. So we now have more fibers. So we went from 1,000 fibers in BOSS to 5,000 fibers in DESI, and we automated the entire principle a little bit. So yeah, now we have automated fibers. You can see them here in these images. And here's a wedge with lots of different fibers, and these fibers now can move and they can position themselves at the exact position where you expect the galaxy to be in the focal plane, depending on where the telescope points to. We also upgraded the telescope, so we went from SDSS to the Mayal telescope. We have a much larger mirror now, a 4-meter mirror. That of course means that we don't have to observe as long, or we can see fainter targets. And originally we were planning for different types of galaxies. So basically we want to measure the same signature at many different redshifts. So at low redshift, we use very bright targets. This is basically a magnitude limited survey. It's called the Bright Galaxy Survey, BGS. And we expect about 14 million redshifts in that survey. Then we use luminous red galaxies at slightly higher redshift. So luminous red galaxies are the galaxies which have been used in BOSS as well. And they have a very, very dominant feature in the spectrum, the 4,000 angstrom break, which allows to get the redshift very quickly, which allows you to observe many galaxies, right? So you look for a very significant feature in the spectrum so that you don't have to observe it for very long. So LRGs are perfect for that. So at this redshift range below redshift 1, above redshift 0.4 has been probed very well with BOSS already, but with DESI we did an even better survey for LRGs. And then above redshift 1, you're sort of running out of LRGs, so you need to pick a different target. So for these, we use the ELGs, and then for even higher redshift, we use quasars. Of course, the quasar density is very low, so for quasars, we will only get about 3 million at the end of DESI. And then at even higher redshift, we use the Lyman alpha forest. I won't talk too much about the Lyman alpha forest, but what we are doing there is basically we are looking at the absorption spectrum for quasars. So the light of these quasars will go through different gas clouds and will be absorbed. So this gives you lots of absorption lines in the spectrum of these quasars, which you can also use to trace the underlying matter distribution. So it's a little bit different to sort of the traditional galaxy survey. And with Lyman alpha forest, you can go to very high redshift. So we can, in principle, go up to redshift 3.5. So we are probing the entire expansion history from basically redshift 0 to something like redshift 3 using these different tracers in DESI. So here's a very busy plot. So the PI of DESI sends this around almost every month. And basically, this shows you the completion of DESI. So the time is on the x-axis, and on the y-axis, you can see the completion rate percentage. So the dashed line shows you the schedule. What are we expected to get to as a function of time? And the orange line shows you the bright survey. So we have different parts of the survey. So for example, if the moon is up or if the sun hasn't completely set yet, so the observing conditions aren't perfect, there's lots of scattered light around. In that case, we only pick very bright targets because we can observe those targets even under suboptimal conditions. So this is what this bright survey is, this orange line. But the main survey is actually this black line, which is when we observe most of our targets. And you can see all of these lines here, they're above the dash line. So DESI is actually ahead of schedule. And DESI is expected now to finish sort of half a year ahead of schedule. So it's fantastic. The instrument works fantastically. And we are now expected to, we added additional layers. So we will now probably increase the completeness of DESI. And there are also ideas to improve the footprint of DESI. So the final data set of DESI is actually going to be larger or more complete than we originally expected, just because the instrument is working just fantastically. So very, very lucky with DESI there. And it wasn't easy. Here's an image from the Mayal telescope over the different telescopes at Kitt Peak in 2022 and 2022. There were many fires in Arizona, and one of the fires actually reached the mountain and destroyed large parts of the forest around the mountain. But luckily, none of these telescopes was destroyed, and the survey was delayed because of the fire. The mirror needed to be cleaned, and there was a delay, but it could have been all over back in 2022. We're very lucky that the fire didn't actually cause any big damages there. Okay, so I will come back to DESI in just a second, but I want to mention that we are very lucky right now because there are actually multiple experiments providing fantastic data sets. And one experiment which is observing since 2023 is the Euclid mission. So Euclid has a bit of a broader science case than DESI. A significant portion of the science case there is focusing on weak lensing. But on the spectroscopic side, Euclid is expected to provide a very similar data set of about 30 million emission line galaxies, so between redshift 1 and redshift 2. And the interesting case here is that the instrumental systematic will be completely different. So I won't talk too much about systematics here, but in DESI, we put fibers on these different galaxies. So the main instrumental systematic, which we have to worry about, are related to these fibers, because these fibers have a physical size, they have a parallel radius. So there are some galaxies which you can just not observe because they can't be reached by a fiber, or the density of galaxies is too high and you don't have enough fibers available. So this is generally known as a fiber collision. And if you're missing galaxies in a non-random fashion, that can introduce systematics, which you have to worry about in your analysis later on. So that's a big problem for DESI, but Euclid won't have any problem like this because Euclid does not have fibers. There are no fibers involved. What you do here is basically send the light through a prism. If you send light through a prism, it gets bent depending on its wavelength. So therefore, if you put a detector at the end of this prism, you have a spectrum as well. And then you can look for emission lines just like you do in DESI. But since you don't deal with fibers, you have no fiber collisions. Of course, Euclid will have other systematics to deal with. But these instrumental systematics in Euclid and DESI are completely different, and that gives you two very complementary data sets. So I think we're very, very lucky here. And here just one fun picture from Euclid. So Euclid on the right-hand side, this is a picture which came out very quickly after Euclid was launched. So Euclid images on the right-hand side, and in DESI, we have to take an image first, and then we pick our targets, and then we put these fibers onto the targets. So we also have to take images, and the image from DESI is on the left-hand side, and the mirror of Euclid is actually fairly small, it's 1.2 meters. But you're operating in space, so you can actually operate your telescope at the diffraction limit. While in DESI, you have a very large mirror, so your diffraction limit is in principle much better than Euclid, but you can't actually operate at that limit because you are on the ground and your photons will travel through the atmosphere and you can't easily correct for that. So these images of Euclid, even so the mirror is much smaller, are much better. And that will help the weak lensing component of Euclid significantly. So there have been no results yet from Euclid, but you should expect the first cosmology results next year. So that will be very exciting. And that is all what I want to say about Euclid. But when I give talks next year, I hope that Euclid will actually then contribute to the science discussion, which I will go towards now as well. So what I want to introduce next is Baryon Acoustic Oscillations. So that's the main observable I want to talk about in this talk. So what are Baryon Acoustic Oscillations? So Baryon Acoustic Oscillations have been imprinted at a very early stage in the universe. So inflation introduced small density perturbations in the early universe. And the universe was very hot and dense. The baryons and photons were coupled through Thomson scattering. And these density perturbations introduced by inflation are supposed to be adiabatic, meaning you have a density perturbation in cold dark matter and in baryons. And because the baryons interact with the photons, you have lots of photon interactions wherever you have a high density peak, and that leads to a photon pressure, and this photon pressure is driving the baryons out of this initial overdensity. So you basically have sound waves of baryons traveling outwards from every overdensity in the universe. And these sound waves, they travel for about 300,000 years. And after 300,000 years, the universe cooled enough so the protons can capture electrons, and then they're neutral. And that means the photons won't interact with the baryons anymore. These two components decouple. And then the baryons basically lose their photon pressure, the driving force, and then these sound waves stop. The photons stream away, forming the cosmic microwave background, and they can be detected by our CMP experiments. And they have this special scale. So the distance these sound waves traveled for these first 300,000 years of the universe existence, this special scale has been imprinted on the distribution of photons, and that can be seen in the power spectrum, and angular power spectrum of the cosmic microwave background. I'm sure you're familiar with this plot here, which shows you the Baryon acoustic oscillation in the photon distribution, but you can measure the same signal also in the matter distribution because the baryons also participated in this. So the baryons also carry the signal, and this has been detected in the matter distribution using galaxy redshift surveys. In 2005 was the first detection, but what I show you here at the top is the detection using this BOSS galaxy survey, which I introduced earlier. So what you see here on the left-hand side is the power spectrum, and this is normalized by a smooth component. So the power spectrum itself has many different contributions, not just the Baryon acoustic oscillations, but many other contributions. And these are just divided out here so that we can just focus on this oscillating pattern here, which has been detected to about 8 sigma in BOSS in each of these two redshift bins. So you might ask, why do we want to measure this signal in a galaxy survey? Because we measured it in the CMB here. So why do you want to measure it again in a galaxy survey? Because the error bars here are tiny. So in BOSS, we measured it with 8 sigma. I don't even know what the significance of this measurement is, but it's much higher. So why do we bother measuring the same signal twice? And the answer is that we measured at different times, right? So in CMB, we're probing the redshift 1000 universe. Here, we're probing the redshift 0.6 universe. And this oscillation pattern, so the wavelength of this oscillation, that's this special scale, which refers to the distance these sound waves traveled in the early universe. So when you measure the wavelength of this oscillation, and then you compare it to the same measurement in the CMB, well, the CMB measured it at redshift 1000, we measured at redshift 0.6, and how this special scale evolved from early times to late times over something like 10 billion years, that evolution depends on your background cosmology. So this is how you are sensitive to your cosmological parameters. This is known as the standard ruler technique. You have an object of a known size, and you measure it at 2 different times, and how this the size evolves over time gives you sensitivity to these cosmological parameters. And there are many details which I'm skipping here. For example, there are these labels like pre-recon and post-recon. So there's something called density field reconstruction, which is used here. So there are many details in the analysis, which for time reasons I will just skip over. But if you want to know any of this later on, please feel free to ask. So what we constrain with Baryon acoustic oscillation are 2 different quantities. This has to do with the fact that we have different observables. As I mentioned before, we have angles, and we have redshift. The redshift gives us the radial distance, and the angle gives us the position on the sky. And with these observables, we measure the angular diameter distance, and we measure the Hubble distance. So we have 2 different observables which we can constrain. So our angular modes constrain the angular diameter distance, and our line of sight modes constrain the Hubble distance. And we always constrain them relative to the sound horizon scale. So this RD. Yeah, and we need to know RD if we want to make a distance measurement with Baryon acoustic oscillations. So along the line of sight, we're just constraining the Hubble distance, which is basically given here by the Hubble parameter. And you can see here on the right-hand side that this gives you access to cosmological parameters. So this is where we get our sensitivity to the cosmological parameters, which is the final goal here. The angular diameter distance is just an integral over the Hubble parameter. So it's a very related quantity, the angular diameter distance and the Hubble distance. And these 2 quantities, even though they are related, they might be slightly different. They might have different sensitivities to different cosmological parameters. So it is actually quite valuable to constrain both of them if you have the sensitivity and you can sort of disentangle these 2. If you can't disentangle these 2, you can still get a cosmological constraint, which is just an average of these 2 quantities. I will talk about this later on. And then, of course, as I mentioned, because you have this RD in here, you sort of need to calibrate the standard ruler. You need to know RD to make an actual distance measurement, because only then you can access these cosmological parameters. So where do you get the RD from? Well, RD has been measured, the sound horizon scale has been measured in the cosmic microwave background. Therefore, it's very natural to combine these measurements with Planck, for example, because Planck will just fix RD, and then you have access to this, and you can directly constrain distances. But you don't have to combine with the CMB. RD can be constrained with other ways. So RD is given here at the bottom, and you can see it depends on quantities which we can actually constrain with a galaxy survey just by itself. So this omega BC, for example, we know this, we can constrain this with a galaxy survey. So what we don't know is this omega B, the physical baryon density. So we need to somehow get a prior on this value, and then we can constrain RD. There's also a dependence on N effective. But if you assume that N effective is just a standard value, then it's basically only the physical baryon density, which you need to get from somewhere. And we can get this from other sources. We don't have to use the CMB. We can, for example, get this from Big Bang nuclear synthesis. So I will get back to this when I talk about the Hubble tension later on. Okay, so let's talk about DESI. Here's the data release 1. So DESI observes in the North Galactic Cap and in the South Galactic Cap. So you see the North Galactic Cap here, the South Galactic Cap on the right-hand side. And these blue circles show you a pointing of the telescope. And the color shows you the density. So in general, we observe each part of the sky multiple times, 5 times in principle, but then these tiles can overlap. So therefore, you can have densities here which go beyond 5. This is 28% of the survey for data release 1, but what I will talk about here is actually data release 2, which is already 67% of the survey. So you can see that large parts of the survey are not complete. And this data set contains 14 million unique redshifts. So this is 7 times bigger than all of SDSS, which is 2 decades of observations. And I mentioned BOSS earlier. BOSS used 1 million galaxy redshifts. So this is a significant step forward. DESI is not an incremental sort of step forward compared to what we had before. This is more than an order of magnitude more. So this is a very significant step forward. And you will see this in the cosmological constraint in just a second. Okay, so let's go to the measurements. Here you have all the measurements for data release 2 of DESI. And as I mentioned, we used configuration space to get these measurements. So we have the correlation function, which I introduced earlier. So this is the correlation function monopole. This is Legendre multiple over the L equals 0. And then the quadrupole is at the bottom here. And you have many different plots here because we have many different redshifts. So at the low redshift part, we have this bright galaxy survey, which I introduced earlier. And then we have luminous red galaxies at slightly higher redshift, and we split that into 3 redshift bins. Therefore, you have LRG1, LRG2, and LRG3. And then you have an overlapping redshift bin where you have LRGs and ELGs, and this is actually the bin which gives you this 14.7 sigma detection. So this is the highest significant detection within all these redshift bins in DESI. And then you have the emission line galaxies. They are also binned in 2 redshift bins. So you have ELG1 and ELG2. And then at even higher redshift, you have the quasars. And then at the highest redshift, you have the Lyman alpha force. So these are all the BO detections in DESI. And I showed you the power spectrum earlier. In the power spectrum, you have this oscillating pattern, and you're interested in the wavelength of this oscillation. If you Fourier transform that quantity and you get the correlation function, then you kind of localize the signal and you're actually looking at the peak. And now you're interested in the position of that peak. And you can see this peak very clearly in these monopole measurements. It has been detected in all of these different redshift bins with very high significance. The lowest one is 5.6 sigma, which is this BGS sample. But we have very high significant detections of this BO signature in basically all of these redshift bins. Okay, so now we can try to constrain cosmological parameters. So see the time. Okay, only 11 minutes left. So first, what we do is we assume a cosmological model, and we start with lambda CDM. So in lambda CDM, the Friedmann equation is given here. The Hubble parameter is basically depending on the Hubble constant and omega m. And that's it in lambda CDM. And we are only sensitive to this quantity, right? So we constrain 2 observables, as I mentioned earlier, the Hubble parameter and an integral of the Hubble parameter, which is the angular diameter distance. So we are basically within lambda CDM, we are sensitive to these 2 parameters. The complication is that there's this RD quantity involved. That's why there's this RD here on the x-axis. So we cannot actually constrain the Hubble constant directly. We always have RD involved, so I will get back to that later on, but we can constrain omega m directly. So if we use only one of the redshift bins in DESI, in this case the quasar sample, then we get this degeneracy here. So our constraint on both of these quantities is actually fairly poor. But the interesting aspect is that if you have these constraints at many different redshifts, then this degeneracy line actually rotates. So the BGS sample gives you this degeneracy line. And then if you look at the LRG sample, first LRG sample, LRG2, the Lyman alpha forest, ELGs, here's this overlapping redshift bin between the LRGs and the ELGs. And if you combine them all, then you get these black contours. And so you can see the individual redshift bins by themselves, they can give you decent constraints, but the overall constraint actually benefits from the fact that these degeneracy lines rotate with redshift. And by combining all of these different contours, you can get very, very tight constraints on both of these quantities. On omega m, we have a constraint of 3%, which is comparable to the constraint on omega m from Planck. And on the x-axis, which is this product of the Hubble constant times RD, we have a constraint better than 1%. Okay, so here is just a comparison of DESI with the cosmic microwave background. This is when I talk about the cosmic microwave background, I have it in some slide here. I talk about Planck and combined with some CMB lensing, which also involves ACT. So this is what I refer to when I mean the cosmic microwave background. So it's written at the bottom here. If I get back to this plot here. So basically, we have Planck here together with ACT in this pink contour, and you can now compare this with the DESI measurement in this plane of omega m versus h0 times RD. And you can see that there's a little bit of a tension here. So the dashed line shows you the data release 1 and data release 2 basically stayed at the same position, but has much smaller error bars. So these contours have shrunk significantly from DR1 to DR2. And there is a bit of a tension here of about 2.3 sigma. If you include the latest data from ACT, you can actually reduce this to 2 sigma. But the CMB and DESI are not in complete agreement. And I'm mentioning this here because that will be important later on when we talk about dark energy a bit more. But the tension is 2 sigma, so it's definitely not a significant tension right now between the CMB and DESI. Okay, so now what we can do is we can make our cosmological model a bit more complicated, so we can introduce curvature. So now the Friedmann equation looks slightly different. We have this term which we had earlier, but now we have one additional term here, curvature, and then our dark energy term is here on the right-hand side. So we have one additional parameter to constrain. But again, if you combine all of the different redshift bins in DESI, then you can constrain curvature just with DESI, and you have here a constraint on curvature. If you take the CMB just by itself, it can constrain curvature as well. So if it has this value of a negative curvature, DESI itself is perfectly consistent with 0 curvature. The CMB Planck points towards negative curvature with not very high significance, but there have been papers written on this negative curvature in Planck. If you combine the CMB with DESI, then you actually get positive curvature to about 2 sigma. So DESI certainly does not support this sort of negative curvature term, which some people might have claimed to have seen in Planck. It actually flips to the other side, detecting something positive to something like 2 sigma. So this seems to be perfectly consistent with 0 curvature. I don't think we call this very significant deviation of some 0 curvature. Certainly no confirmation of this negative curvature, which some people saw in Planck by itself. Okay, going to the Hubble tension. So as I mentioned, we cannot constrain the Hubble constant with DESI by itself. We need to calibrate our standard ruler. We need to know this RD value. And as I showed you earlier, if you want to know RD, you need to constrain the physical baryon density. And you can get that value from Big Bang nucleosynthesis. And if you combine DESI with Big Bang nucleosynthesis, you can get a very tight constraint on the Hubble constant with an error bar of only 0.8%. And this is the value which you will get from DESI combined with Big Bang nucleosynthesis. We can now compare that with Planck, and Planck has a measurement of the Hubble constant within lambda CDM, which is given by this value here, which is an error bar, which is very comparable to DESI. Yeah, so you really have 2 data sets here, which can constrain some cosmological parameters with very, very comparable uncertainties, which is very unique. This is not something which was true even a couple of years ago. So DESI really allows you now to have these fantastic comparisons with the CMB at an equal footing. These 2 values are not in perfect agreement, so the 1 sigma uncertainties do not overlap of these 2 measurements, but they're very close to each other. There's certainly no significant tension between the value measured by DESI plus Big Bang nucleosynthesis and by Planck. And you definitely have a very large tension with this large value of the Hubble constant measured by Shoes, which is around 73. There's a 4.5 sigma tension with this Shoes measurement. And this 4.5 sigma tension does not involve any information from the CMB. You might argue that it involves a constraint on N effective, because I showed you earlier that RD does depend on n effective, and we fix a standard value. So you need to be aware of the different priors which go into these measurements. Also, the Hubble tension still exists, basically. Now we can look at dark energy. So we just introduce a new parameter here. So we remove this curvature term again from the Friedmann equation. Now our Friedmann equation has an additional term here, which basically parameterizes time evolution of dark energy, and it uses this dark energy equation of state parameter to parameterize this time evolution. So DESI just by itself can constrain omega m and this dark energy equation of state parameter, and it gets a value which is fairly consistent with -1. And if you put -1 in here, then your exponent is basically 0, and you remove this time dependence, and you end up with a cosmological constant. It's a little bit larger than this -1 value, which the cosmological constant wants, but just by a little bit more than 1 sigma, so no very significant detection here. If you combine with CMB and supernova data sets, you can reduce the error bar by a factor of 3, but again, you find something which is fairly consistent with a cosmological constant. So now we can make it more complicated, can introduce not just a time-dependent dark energy term, but also a time-dependent dark energy equation of state term. So this is usually parameterized with this parameterization. There are many different ways of how you can parameterize this. And of course, this is a purely phenomenological parameterization. If you want to actually learn something here, you need to map this to an actual dark energy model, which I won't do here. But because there is no obvious dark energy candidate which we can use here, so therefore these phenomenological models are actually very, very useful to just try to see whether the data prefers a deviation from a cosmological constant. So this then gives you a Friedmann equation, which has this fairly complicated dark energy term here, where you have these two additional parameters, omega naught and omega A, and omega A parameterizes this time evolution of the dark energy equation of state itself. So if you take the DESI DR1 results, you get these dashed lines, and with DESI DR2, the constraint itself hasn't shifted much, but the contours have shrunk quite a bit. But you can see that the DESI results are consistent with omega A 0 here and omega naught -1, which is a cosmological constant. So the DESI data is at least a 2 sigma consistent with a cosmological constant. But now what you can do is you can combine DESI with the cosmic microwave background. And if you do this for DR1 and DR2, you get the dashed line for DR1 and the solid contours here for DR2. And now you can see that the cosmological constant is actually outside of this 2 sigma contour by a significant amount. So you actually have now a tension with the cosmological constant at 3.1 sigma. So that is a bit more significant than these 2 sigma tensions, which I talked about so far. So now you can try to combine with even more data sets. So for example, you can combine with supernova data sets. Here we combine with 3 different supernova data sets. So Pantheon is a data set which has been around for a while now. It's been widely used. And if we combine with the Pantheon data set, then we get these blue contours, which actually reduces the significance. So we had 3.1 just with combining with the CMB. If we combine with Pantheon, we go down to 2.8. So if you want to believe in evolving dark energy, that should be a red flag for you, because if you combine with more and more data sets, you would expect the significance to grow. In this particular case, it actually reduces. So that's something to keep in mind. If you combine with another supernova data set, for example, this DESI 5 supernova data set, which is the most recent supernova data set we have available, then the significance grows to 4.2 sigma, which is now very significant. So basically here you have to pick what supernova data set you want to use. You can get very different answers depending on the supernova data set you want to pick here, and I'm no expert in this. So in DESI we just chose all of them, and it's not on DESI to make a decision here. So unfortunately there's no consensus here right now from the supernova community, but there are sort of different aspects. These supernova data sets are not exactly identical, but they are correlated. So the low redshift part of the low redshift supernovae in these samples are very similar. So there are some correlations here as well. So it's actually quite interesting that you get sort of these different answers, and maybe there will be a more clear answer in the future. So we can look at, yes, Adam, you have a question?
Oh, yes. Well, I was just going to make the point about the different supernova data sets that there are some differences between them, but I don't think the differences between supernova data sets are any larger than the differences between, let's say, CMB data sets, or even that we see between BAO, SDSS, and DESI. I mean, all, different experiments have fluctuations, but I mean, for example, in the CMB, Planck and ACT differ by 2.5 sigma in the most recent ACT paper. And, I mean, we like to understand that, but I guess I'm going to defend supernovae a little bit and say the fluctuations you see experiment to experiment aren't much different than what I see in other experiments.
Fair enough. I would say that um, there is a big difference between a 2.8 sigma significance and a 4.2 sigma significance. So maybe a question for you: should I trust the DES supernova sample, and should I just go with 4.2 sigma, or should I take the Pantheon result just because it's more established?
Right. I mean, formally speaking, DES and Pantheon Plus are most similar in that they use, the same tools for fitting. It's Union 3, which is the most different from them. So, I guess I would say that Pantheon Plus and DES bracket Union 3. So I think, I would sort of at a high level say something in the middle is probably right. That this is still probably in the mid 3 sigmas evidence.
Okay, interesting. All right, let me just finish the slides because I think I'm already over time. So I think I need to skip some of the slides here because I was a bit too ambitious here. So here you can basically look at sort of how robust is this tension with your cosmological constant depending on the data sets you're looking at. So the first step, what we can do is we can reduce the CMB just to the CMB prior. So the parameters which the CMB can constrain best, which is this theta star, omega B and omega BC. And if we just use those, then you can get a preference for this evolving dark energy of 2.4 sigma. So your preference goes down, but it's presumably more robust because you're removing a lot of aspects of the CMB, which involves a lot of these anomalies, which people might talk about in the CMB. So you have a sort of a preference for this evolving dark energy, even if you reduce the CMB to this distance priors. So that's step one. The other aspect is related to the supernova data sets. You can remove the low redshift part of these supernova data sets. The low redshift part is fairly important because you need to, in the supernova data sets, you need to calibrate your high redshift supernova with low redshift supernovae. And these low redshift supernovae, as I mentioned, they are very similar between these different supernova data sets. So if you remove these low redshift supernovae, you do remove a significant portion of your significance, these 4.2 sigma significance, which you have with this DES dataset, for example. So you do depend on these low redshift supernovae quite a bit if you want to claim 4.2 sigma. Your significance reduces to 2.4 sigma in this case. And the other aspect is you can also replace the CMB with the lensing result from this, and this would still give you a preference for evolving dark energy at the level of 3.3 sigma. So basically there's some sort of reliance. So you can replace some data sets. You can, for example, completely remove the CMB and you can still find evidence for evolving dark energy. So this is sort of interesting. So this is quite interesting. So I want to go through this fairly quickly if there's time. But if I take too much time, you just interrupt me because at that point I can also skip to the final slide. So what this shows you, there are lots of plots here. So let's just focus on the left-hand side. The left-hand side, the points show you the data points, the isotropic BO measurements, and you can see the anisotropic measurements here as well, but let's just focus on the left-hand side, the isotropic measurements. The CMB best fitting line is shown here as the black line, and you can see that it doesn't describe the BO measurements perfectly, right? So there are lots of data points below this line. And then you can, the plots on the bottom here show you the supernova data sets, the 3 different supernova data sets. But again, let's just focus on the left-hand side, which shows you this DES supernova data set. So if you take the CMB, then you get omega m of 0.31. This is this solid black line. You can also fit a lambda CDM model to the BO data points, and this gives you a smaller omega m. And this is this 2 sigma tension which you have between the CMB and DESI. But you can definitely find a lambda CDM model which describes these BO data points perfectly well. You can also fit the DESI and the CMB together, and you will get something very similar. But then you can also find a lambda CDM model which describes these supernova data sets very well. But you can see that that model isn't a very good description for the BO data points, and you get a very large omega m here. So you can basically describe all of these individual data sets with a lambda CDM model, but these lambda CDM models, they don't agree with each other. So that's the problem. So now you can go to WCDM, let's skip that, because if you go to W0 WA CDM, then you can find a model which describes the BO data points and the supernova data points at the same time with and basically resolves this tension which you have within lambda CDM. So I think this is quite instructive. And then I should say another big red flag, if you want to believe in this evolving dark energy, is that the theoretical support for evolving dark energy is fairly weak. And this has to do with the fact that the preference right now seems to prefer these values of the dark energy equational state parameter, which cross to very negative values, more negative than -1, which is this phantom regime. And that violates the null energy condition, which you can bypass in many ways. But if you want to bypass this, you might need to modify GR, or you need to do something more sophisticated. So a simple model to replace the cosmological constant usually doesn't want this phantom regime. So therefore, right now there is no easy dark energy or simple dark energy candidate which has emerged, which can explain this preference by these data sets. So this is, I think, one of the biggest red flags which I see right now with this evolving dark energy. There's lots to say about the neutrino mass, but if you want to talk about the neutrino mass, I'm happy to talk about it, but let me just go to the final slide. So DESI and the CMB are in slight tension, and I showed you this tension, which is about 2.32 sigma in omega m, in this omega m versus h naught times RD plane. And then there are other tensions, for example, the neutrino mass. There's this weird preference of negative neutrino masses. And these sort of tensions between these fairly robust data sets, I would say that the CMB and Baryon Acoustic Oscillations are the 2 most robust data sets which we have available in cosmology. And if these robust data sets show these tensions, that might be a sign that something is not quite right. And we can see that these tensions basically can be resolved by this evolving dark energy. And I mentioned that that there are some red flags here. So I myself wouldn't say that I'm completely convinced yet by evolving dark energy. I think it's very intriguing, but I think we still need to investigate this further. And the good news is, of course, that there's much more data coming. So at the end of this year, we will have the DESI year 5 data set completely collected. And then there is already a 2-year extension scheduled for DESI. So DESI will basically observe till 2028. So there will be lots more data. The DESI data set will grow in completeness and grow in the footprint, or the sky area will also grow. So there's lots more data from DESI coming. And hopefully that will resolve this issue or increase the question mark. Okay, and then I should also mention that this talk is, of course, depending on a very large collaboration. This is not my work. This is the work of a very large collaboration with many funding agencies involved. And I'm just presenting these results as a representative of this very large collaboration. Okay, thank you very much.
Thank you.
Happy to answer questions.
Yes, thanks for the nice talk. Do you have any questions, Erin?
Yeah, Florian. And the big problem here, well, thanks for the talk first, is H0 tension, right? In 2022, we wrote a paper where we more or less studied mock DESI data, and we showed that if W0 was greater than -1, you would really struggle to push H0 up. So this is a continued, so that's your big problem. And you can see it in the combination of CMB plus BAO plus supernovae. So basically, as W0 moves further away from -1 in the upward direction, H0 typically goes south, right? So that's the first comment. And it's the question I have for you after you address that is, why do we see a no dynamical dark energy signal in full shape modeling, but we do see it in BAO? There seems to be an inconsistency between these two different pipelines. So that's the question. Those are comments. Thanks very much.
Okay, so first addressing your comment, this is true. I think I forgot this to mention, but yeah, if you want to resolve the Hubble tension, this evolving dark energy is not going to help you at all, because the Hubble constant is actually, I think the Hubble tension is actually increasing if you introduce this evolving dark energy. That's a very good point. So the full shape modeling from the year 1 data set did not tell us much more about evolving dark energy. This just has to do with the fact that if you want to constrain W0 WA, you get most of the information from Baryon Acoustic Oscillations. This is not entirely true. This is just true within the priors and the analysis setup which we chose for the year 1 analysis. So if you include the full shape modeling, the preference for evolving dark energy was going down a little bit, but basically there wasn't much information there, right? So the full shape modeling wasn't contributing much to W0 WA. But you're right that once you include the full shape modeling, the preference was going down, and that should be a concern. But I would say that there isn't much information which was added by the full shape modeling in the year 1 analysis.
Thank you. Pieros?
Thanks for the nice summary and presentation. I would have a question about you were presenting in the collaboration that there were tests of different flavors of dark energy, but there is always the worry of modification of gravity. Have you been testing parameterizations in this direction, and if there is a combination of modification of gravity and a flavor of dark energy that fits the data as you nicely saw?
Yes, so there have been, unfortunately, I don't have any plots here, but there have been many tests for different modifications for of gravity, of generativity. I don't think there was anything super convincing there. I have to remind myself whether there was, I think there were some 2 sigma preferences for some parameterizations, but I can't remember which ones. I don't think there was anything very convincing there.
Okay, thank you.
Florian, very nice talk. I agree with your point. I think most strongly the summary point that about the growing incompatibility between the different data sets when interpreted with lambda CDM, and it's certainly much harder to go to a particular solution like evolving dark energy or many things like that. I guess my question for you, I mean, you're both on the data side, a little bit on the theory side as well, is do you think it's possible to sort of reach a conclusion like that first, that things are incompatible without having a solution? I feel like sometimes I see it's hard for the community to sort of hold on to one thing, that things aren't compatible, without jumping to a solution, and then whether that solution is acceptable or not.
Yeah, I think this is the biggest issue, which, for example, we have in the Hubble tension, right? So people don't know what to do with it because we don't have a clear model, a convincing model, which would just bring these measurements in agreement. And I think the same is here, right? So if we can't come up with a convincing model which makes sense, which solves these tensions, then people won't believe in it. And I think I won't believe in it. I think we need to have a model. Otherwise, I don't know what this is.
That's interesting because I mean, there's so many times in science, I don't mean to be philosophical, but where we see a problem, but we don't have the solution. And I guess what you're saying is you can't really believe in the problem unless you see the solution.
Well, I think
as an observer, I think we can pause at the problem without having the solution. Sometimes it takes decades to have the solution.
Well, I think in 1998, I think the thing was that we had a model which very quickly explained the tension which you measured, right? I think this convinced people, even though it wasn't a very convincing one. So I think dark energy wasn't
Right.
a very good model.
It was a stand-in, yeah.
But it was a sort of a model which sort of people raised before. I mean, it had some good aspect, and I think that's all we need. We need some sort of replacement for
You need a
lambda-CM.
story, you're saying, to believe.
Yeah, because
Right.
otherwise it's always the nagging feeling. Cosmology is always systematics, right? So it could always be that you just don't understand what you actually measure there. And
Right. I mean, there's just so many times in the history of science, the precession of Mercury, solar neutrinos, where, the clue was seen and the answer wasn't known immediately. And, I believe this could be done stepwise, sort of in some way, but I appreciate your points as well.
Yeah, no, I think it's a fair point. I think the only time when we actually learned something was when we were able to, when Albert Einstein was able to explain the weird measurement, right? This is when we actually learned something. I think the tension, I don't know whether anybody learned anything there, but fair enough, yeah.
Thank you. Frederick?
Unfortunately, there's nobody listening from the New Zealand school. There is a model which in principle explains these kinds of variations, which is the timescape model from Wiltshire, which is never mentioned. Is that on purpose? You don't think that that's an alternative or what?
I don't know much about this model, so I don't think I can.
It basically uses generic general relativity with no dark energy and explains the effects as being due to the situation that you can't impose a background metric. You have to let the metric basically create itself.
Okay, I think I'm not quite equipped to answer this question. I need to look at it.
I'm
If you
not
want to
a
send me
GR
some,
person either, but I know this model exists, and I know that it has been shown to work very, very well to explain the supernova data, but it's not usually mentioned, and so I was wondering why.
Yeah, in my case, I think I don't think I know enough about this model, but it would be great if you could send me the reference.
Just
which
look
showed
up
that this-
Wiltshire and timescape.
Perfect. We'll look into this. Thanks.
Thank you. Pieros again?
Thanks. Regarding the ruler, usually in order to make estimates about H naught and other parameters, you need to have a calibration on RD, and usually you take BBN priors. This is usually done from CMB, but is there other kind of experiments that they can give us BBN priors, possibly from Large Hadron Colliders or some other kind of test, where you can test if this is calibration that you are doing with BAO is valid?
From a Large Hadron Collider, I'm not aware that you can measure. I'm not entirely sure how you would measure this from a Large Hadron Collider.
The idea in LHC, you create energies that they are very close to the energies of the Big Bang, so you can have some kind of estimates, but I'm not sure if there are estimates on that. I was wondering if there's another source of prior on BBN that you can use for the calibration. So
Yeah, so what you're referring to is this value of RD, and as I mentioned before, this omega B here is the uncertain. This is a parameter which we don't know from large scale structure survey. So we need some sort of prior on this value, as PRS mentioned, that comes from Big Bang nucleosynthesis, or it can come from the CMB. And these are, to my knowledge, the only two sources where you can get this from. I don't know about a third source. It would be, I mean, I think I'm convinced that this is not the issue, given that we get so very similar results depending on whether we use it from the CMB or for Big Bang nucleosynthesis. It would always be good to have a third one, but I don't know where this would be coming from. I think the more interesting part is that there are also other dependencies here, which you might need to think about.
Okay, thank you.
Thank you. I think there is a final question in the Q&A. So Manosh is asking, does the BBN also put independent constraint on RD, or is it just focusing on an effective baryon density? The number 147, does it change with BBN?
Okay, so BBN constrains the physical baryon density, not RD, right? But that if you know omega BC, and if you make some assumption about n effective, then you basically constrain RD with just knowing about the physical baryon density. Right, so you cannot constrain RD from Big Bang nucleosynthesis alone.
Okay, thank you. Then there is another question related with the question pointed by Eoin. Did you consider a W dark matter model with a non-phantom prior, W larger than -1? And if yes, what was the result consistent with the cosmological constant? Thank you for the very good presentation.
That's a good question. I think there was a model considered like this in a supporting paper which we published with the DR2 results. I don't really recall. I think the issue there is just that the delta chi-square you're getting from these models is always less than what you get with this phenomenological parameterization W0 WA. So we have 3 sigma significance there. So if you reduce that, then you might only end up with sort of a 1.5 or 2 sigma shift. So you're only reducing part of the tension. So yes, you can come up with models which don't enter this phantom regime, which can also improve your fit. But that improvement is not the 3 sigma, so what I talked about here. So, and the values you can find in this paper, I don't recall the exact numbers.
Okay, perfect. Thank you. I think there are no other questions. So we can thank Florian again. Thank you so much.
Thank you very much.
Thank you. Bye-bye.
Bye, everybody.